My name is Eva Daly, and I will be talking about gravity today. This program is based on my book, The Science of Consciousness. The modern understanding of gravity started with Newton, who noticed that the falling of an apple and the movement of a planet is governed by the same physical law. In the early 20th century, Einstein recognized that the apple is not pulled by gravity, but it is following the field curvature of space. Here I intentionally use the word space rather than space-time because if you remember from my last program, space-time is a faulty concept in physics. The essence of general relativity was put most elegantly by Wheeler, who said that matter tells space how to curve, and space tells matter how to move. However, one of the goals of physics in the past 100 years has been the unification of general relativity and quantum mechanics. And in quantum mechanics, a measurement actively changes the system being measured. So we do have to change Wheeler's words accordingly. We have to say that a particle curves space, and the particle also changes. Of course, nobody knows what a particle looks like. So here in the following slides, I will use different representation for particles depending on the point I am trying to make. Also, the field curvature cannot be drawn properly in 2 dimensions. For this reason, it is not consequent everywhere, and it is just symbolic and representational purposes only. In our first slide, Cy indicates the particle, and from A to F, the particle is shown from negative to positive curvature field. Close to the white holes, the particle horizon is information free. As a result, the particle will be smooth and compact. The spatial field will curve negatively. It will curve away from the particle. Their combined effect will lead to a spatial vacuum. The universe abhors vacuum, therefore this will lead to a new space creation and the spatial expansion, which is called dark energy in physics. And this concept very conveniently explains the source of dark energy. When we look at a particle close to the black holes, then we find that the particle horizon is information saturated. It will develop energy minima and maxima, and as a result, the particle will be wrinkled and stretched out. In contrast, the spatial field curves positively. It will curve toward the particle, and the combined effect will lead to a spatial tightness, a tension that is experienced as excess gravity and termed dark matter in physics. Now, when we look at the global shape of space between the poles, then we find a smooth topology formed by individual particles as they orient between the expansion and contracting potential of space. The here A indicates the white holes, C shows the black holes, and between them Euclidean areas marked by B serve as a fulcrum between the opposing spatial dynamic of the pores. So this way, the white holes and cosmic voids expand space, whereas the galactic regions and the black holes contract it. But we can also model the large-scale picture of space as a balloon, where the white holes which curve into the fourth dimension increase dimensionality of space and therefore lead to a spatial expansion, whereas the black holes which decrease dimensionality will contain it and slow expansion. So the black hole's immense field strength will be the outer boundary of space. And this picture of the universe is identical to the ADC CFT anti-de Sitter conformal field theory correspondence proposed by Maldacera, which recognizes the symmetry between the opposing dynamic of these different dimensional regions of space. It is also a coherent idea with the 2012 paper by Almairi and colleagues that proves that the black holes form the forbidding boundary of space. So far we looked at the large-scale structure of space, but when we look at individual particles, that we find that particles can have two possible quantum states, upspin and downspin. And the spatial field can also curve two ways, positively, which is increasing field strength, or negatively, which is decreasing field strength. Now, the Page and Wouter mechanism of static time states that the global picture of space maintains the static state. As a consequence, this determines that an upspin particle, which gives up information, necessarily forms a negative field curvature, which increases spatial volume, and the downspin particle, which accumulates information, must reduce spatial volume by forming positive field curvature. Now, if we see these particles, here a downspin particle is shown, which is losing dimensionality toward the field. The spin direction is indicated by the gray arrow, and the particle's influence to increase field strength is shown by black arrows. Here, so the next slide shows an upspin particle which gains dimensionality toward the field, and the particle's spin direction is shown also by the gray arrow, and the particle's influence on the field is shown by black arrows as it curves the field negatively. When we put two particles side by side, we find that they will form identical field curvature. Here on the A we show two downspin particles. There is an energy maxima forming between them. It can be shown that the situation is the same between two upspin particles. The principle of least action dictates that an up and down spin particle must be side by side, which form the minimal energy conformation between them. Here it's shown on the B, and this we recognize the Pauli exclusion principle, which states that two identical fermions cannot occupy the same space simultaneously. And when we look at larger section of space, we find that the greatest speed of interaction will occur in the region where the concentration of the particles is greatest, as the particles will vigorously try to find the minimal energy configuration between them. So this way, the spatial field differences in space will be enhanced as the greater curvature region, a particle that is sitting within greater curvature region, will more likely to form downspin, and its partner particle that is sitting within lesser curvature region will more likely to form upspin. And when we look at this process over larger scale of space, we find that the regions with already greater curvature will gradually increase the spatial field strength. On our slide, the field strength will be increasing toward the left along the white arrow, and the field strength will be decreasing toward the right along the black arrow. This way, large galactic objects will develop an onion-like spatial curvature structure inside them, which doesn't end at the edge of matter. It will expand into free space as different field lines overlap and merge. They form common field which directs the movement of objects even on the larger scale, and also it will direct the movement of an apple that is falling from the tree. The hypothesis is elegant and simple. It doesn't require the introduction of special physics or special particles for its operation. It can explain dark energy and dark matter as simply the result of the opposing dynamic of the spatial structure along the poles, and it explains gravity without the need to introduce a new particle such as the graviton, as simply the result of the Pauli exclusion principle.